and double checking the audio is good. And now we can officially get the class started. This is one of the shortest module ever. This is it. So all it does is to say, how do we return a value from a subroutine? And to be more specific, we're returning a scalar value. A scalar in C and C++ refers to an integer, a float, a double, a pointer, okay? Something that cannot be quote unquote divided into smaller components. So a structure would not be a scalar. An object of a class would not be a scalar. An array would not be a scalar. Is that okay? So scalar is basically something that is, undividable. Okay, it cannot be broken up into smaller components unless you start to use bitwise operators. Okay. So for our purposes, okay, we will just say that integers. Okay. So in the case of an integer, most compilers for most architectures just pick a single register, okay, out of all the registers to store the return value, which is of scalar type of some sort for a subroutine. So for the for text toy processor for TTP, we'll just choose register A. So it is the same thing as register D being the stack pointer. It's just a convention. Nothing makes register D any different from all the other registers. Nothing makes register A any different from the other registers. It is really just how we use it that makes one the return value and the other one the stack pointer. So is that part understood? Okay. All right. So we'll take a look at the C subroutine. Okay, this is a really, really simple subroutine. The name of the subroutine is FIVE, and the value that it returns is a constant of 5. In other words, it's a pretty useless subroutine, other than being used to illustrate how do we return a particular value from a subroutine. So the code underneath, okay, and let's see, it's already in, oh, this is maximized mode. Nope, this is maximized. There we go. I'm just trying to move the screen up a little bit, just so the people in the back can see it. So let me resize it. There we go. All right. So the corresponding assembly code is just that, okay? All we do is LDIA5, which means we are loading the immediate quote-unquote constant value of 5 into register A. That's my return value. The next 3 lines we have seen already on Monday. That is the sequence of instructions to return from a subroutine. It has nothing to do with returning a value. It only has to do with, let's get back to the caller and continue execution in the caller. So those three instructions, the first one is LDB in parentheses D, which means we are grabbing the byte that the stack pointer is pointing to right now and put it into register B. So line 3 is basically retrieving a byte from the stack. So once that byte is retrieved, we don't need it to be on the stack anymore. It is quote unquote used. So on the next instruction, which is line 4, we increment the stack pointer because remember the stack grows downwards. Okay, we start at a high location. The stack pointer points to a high location initially, and as we have more items, it points to lower and lower and lower locations. So once we have used a particular location and go like, we don't need that anymore, then we increment the stack pointer so that that single byte can be reused again later on by other subroutines. Is that okay? All right. So on line 5, okay, JMPB, okay, we talked about this on Monday as well. So the only thing JMPB is going to do is to copy register B to the program counter. Now the program counter dictates where we are going to get the next opcode. In other words, by changing the program counter, we are changing the path of execution. In other words, on line 5, after line 5, where this code is going is whatever we have stored earlier on the stack that was pointed to by the stack pointer. It's not anymore because we have just incremented the stack pointer. So is that part okay? Are there any questions about this chunk of code? No questions? All right. So what we'll do is we're going to go take a look at an example where we call 5 twice, and we add it up and then put it into another register and see how that code is going to look like. So please ask questions when I work on the example, because this is a perfect chance for you guys to kind of just slow me down and have me to explain the concepts in various ways, because we're looking at examples. So let me present the C code first. So in the C code, this is all I want to do. Registers are not local variables, so at this point we don't have the concept of local variables, so we're not going to go there. So we'll just say that register C is the return value of 5 plus the return value of 5, and that's all I want to do in main. And then 5 is just like what we talked about. It returns an integer, and it's always returning the constant of 5. So this is the program in C, and I'm going to implement it in assembly. Do we have any questions about the C code first? Okay, so on line 3, C is neither a local variable nor a global variable. It is a register. Okay, and there's no way in C to truly designate something is a register. You can actually use the word register as a keyword in front of an int declaration, so that the compiler will say, oh, I see you want me to try my best to use a register for this particular variable, but it's never guaranteed. Okay. All right, so now we want to look at, okay, what does it look like in assembly code? So I'm going to use a new window for that, so this way we can show both the C code and the assembly code at the same time. So in terms of the assembly code, the first thing we do is a subdd, and all it does is to initialize the stack pointer to 0. Okay, it's just a tricky way to do it. You could have done just LDI d comma 0 if you want the more obvious way to do it, but subdd is one byte shorter than the other one, and it is also faster too. It's faster because it doesn't need to access the next memory location. The opcode itself is only 1 byte long instead of LDI D0, which is 2 bytes long. So that's why from the optimization perspective, subdd is actually a better instruction, although it looks kind of more obscure. All right. So that typically is not considered a part of main because it's assumed to be done before main gets control. And by the way, this label main has no actual meaning other than documentation. In other words, I'm not jumping to main. I'm not going to load the label of main into something. It's really just here to designate this is the beginning of the main program. Okay? Because nothing is going to call main in assembly. Main is just it just starts execution without being called. Okay, so when you look at line 3 in the C code, it looks like I can't really do anything about C unless I call 5 first, right? Because with any type of assignment operation, you have to evaluate the right-hand side first. Whatever the value of the right-hand side is, you copy it to the left-hand side. So you can't really do anything until you have evaluated the right-hand side. So in this case, the right-hand side is the sum of the return values of 2 instances or 2 calls to 5. So we'll go ahead and see how we can do this. So now we have to call 5. And we'll just say, let's call 5, okay? And to call 5, there are a few steps. The first thing is we have to set up the return address first on the stack. So this time we don't have a choice but to use LDI. And register A, even though it is used for return value when we get to the end of a subroutine, otherwise it is kind of free for use for other purposes. So until you're really at the end of a subroutine that returns a particular value that is scalar, you can use register A just like any other registers, no problem. Is that okay? All right. So we just put A into main return 1 into A. And then this is the way I code. I just immediately define the label. And then what we do is we decrement the stack pointer, okay, to allocate space for return address. And then we store the return address to where the stack pointer is pointing to. So that's stda. So that means we have just pushed the return address on stack. So now that we have the return address already on stack, we can now continue execution in the subroutine, which is done by a very simple jump. Okay, so we now jump to 5. When 5 returns, it's going to be here. In other words, at this point, A has the return value of 5. Is that okay? So without even writing the subroutine F, you can assume the return value of 5 is in register A when we get back to main. That is the convention. It's an agreement between the caller and the callee. Is that okay? So it's not enforced by the processor. It's not enforced by the assembler. It is simply a convention. It's an agreement between the caller and the callee. Are we doing okay? All right? Okay. So now I cannot use register A anymore. Okay? In fact, I have a problem now. So let me just go ahead and do the other part here. So knowing that I cannot use register A for this purpose, I'm going to do a LDI, let's say B, of main return 2, the other return label into main. And we'll do exactly the same thing and push that on the stack. So we decrement D again, ST store into D, register B this time, and then JMP5 the second time. This is the second call to 5. So we also know that at this point A has the return value of 5. Okay, so in this example, you can go like, we don't really need another call because we already know what 5 is going to return. Well, that's only because you can see the source code of 5. If you cannot see the source code of 5 on line 9, you cannot make the assumption that 5 always returns a constant of 5 as a value. So that means you cannot just say that, oh, these two A's have exactly the same value. Okay, we just add A to A and we are good. Okay, we can't make that assumption. So that means I have to do something to remember the return value at this point, because it's going to be overwritten by the second call to 5. Is that making any sense? So register A, as it is on line 9, 10-ish, okay, is not maintained on line 16, because the second call to 5, or the second call to any function that returns a value, is going to override register A. So that means we have to somehow remember register A so that by the time we get to line 16, we can use the first return value of 5 and add it to the second return value of 5, which is now currently in A. You go like, well, if I look at this code, it looks like register C has not been used. Okay, so it looks like we can just do a CPR. Okay, so on line 10, I can do a CPR C, comma A to copy register A to register C. Then we can use register C on line 16 and add register A to it, and then we are done. Well, that's a problem as well. Why is that a problem? Because whenever you call a subroutine, the convention or the agreement between the caller and the callee is the callee can modify any registers. Okay? So that means you cannot assume registers to be unchanged when you call a subroutine. You have to assume that the subroutine is going to change, it's going to mess up all the registers, except for register D, which is designated as the stack pointer, and register A if it has a return value. But register B and C are not guaranteed to maintain their values by a callee. Okay, so we cannot use register C either. Then what do we do? Well, we have a stack, don't we? So one thing that you can use a stack for, in addition to storing and using the return value, return address, is you can stash anything you want to store onto the stack and later on retrieve it. It's kind of like a little knapsack. Okay, you can just say, oh, I kind of need this later on, make a copy, throw it into the backpack. Okay, when you do need it back, then you pull it out, but you have to do it in the right order. So what I'm going to do now is I would push return value of first call to 5 on the stack. Okay, how do we do that? Well, if you want to push something on the stack, you always start with decrement D to allocate the space, and then the second instruction is TD, and then whatever register you want to save. In this case, the register is A, so now we push A on stack. Good. So that means by this time, okay, by this time, the stack pointer, or register D, points to the return value of first call to 5 on the stack. There we go. Does that make sense? Is that okay? Now, certain parts of this may not seem to make sense because we push it on the stack and then we push the return address on the stack. So when we get to this point, aren't we expecting the return address to be on the stack instead of the saved value of register A?
It is, because it was put in last, so first out. So when you leave
5,
you'll be back aiming at that 5 you saved.
That is correct. So subroutine 5 or the callee is responsible to remove the return address. So the caller puts it on the stack, but the callee is the one that removes it from the stack. So that's why, when we get back to main return 2, we can assume the stack pointer is now back to pointing at the saved return value of the first call to 5. Are we doing okay so far with this? Okay. So if that is the case, we can now retrieve that. Okay. So the next thing is pop to register C, because I want to do all the calculations in C. So to do that, we first do an LD instruction, LD to whatever register you want to save to, or you want to store the popped value. Okay. And then the next thing we do is increment D. So the D is now, so the stack location is now deallocated. So deallocate stack space, just used. Okay. So now that C has the return value of the first call to 5, and register A still has the return value of the second call to 5, I can add them together. So when I say add CA, then I have the sum. Okay. So this is the sum, and we're done. So are we kind of doing okay so far with this code? From main's perspective. Okay. What about 5? Well, 5 is just the same as what we talked about a little bit earlier. So you just do a LDA 5, which specifies the return value. Since this is the return value, then you just use the same 3 instructions to get out of a subroutine, which starts with a LD. Now this time I cannot use A anymore because A is now the return value. So I would have to use, say, B. Okay, so we retrieve return address from the stack, increment D to free one location on stack, and then JMPB to continue execution in the caller. Is that okay? Are there any questions about this code? Yes or no? Are we good to move on, or do you guys want to spend more time on this program? Okay, we're good to move on. All right, good to have a confirmation. Thank you. All right. So now we can move on, and the next one. So we are kind of done with returning values at this point. Okay, but I'll keep that slide on because we might want to refer back to it from time to time. Uh-oh. So what we'll do next is to move on and talk about parameters and local variables. This is a longer slide. When we talk about parameters and local variables, it's a little bit trickier. So we'll take a look at the notes here. It's a little bit longer than the previous one, and yet it is not too long. So the first thing is about parameters. You cannot really predict how many parameters there are in a function call. Okay, it's not like, a scalar return value, which usually can fit into a single register. The number of parameters can vary. Okay, you can have simple subroutines that have no parameters, okay? Or you can have like 20 parameters. So there's no easy way to say, well, can we use registers to pass parameters? No, because we only have so many registers, and what if there are more parameters than there are registers to use for passing parameters? Can't do that. What about reserving static locations, in RAM, so that we just use those locations to specify the parameters? And how about that approach? It doesn't work in recursion. So where else can we put our parameters? The stack. So the stack is also a place where we put parameters when we call a subroutine. Okay? And it has to be done by the caller, because the caller is the one who knows what what arguments needs to be passed. So what we'll do is we'll take a look at this example here. And this one is, it only gives you, okay, there we go. So it gives you the C code and then the assembly, it gives you the assembly code and then the C code. So we'll take a look at the C code first, which is this part here. Do we have any questions about the meaning of the C code, the subroutine called subtract? Pretty simple, okay? It's got two parameters, x and y, and the return value is really just x minus y. Okay, looks pretty easy. So now the question is, how do we set this up, when we want to make this call? So this is something that's new. I'm trying to do it in a slightly different way compared to previous semesters. So I'm going to try to use my tablet to draw a picture of how the stack should look like when everything is set up. Okay? I might have that picture somewhere else too, but definitely not around here. All right, so let me go get my stylus and start up the program that shows the tablet. Uh-oh, I don't have my command line here. Just move it over. There we go. And okay. So whenever I draw memory, I always assume high memory is on the top side, low memory addresses is on the low side. So that's kind of convention that I use in my classes. So now the question is, how do we set up those parameters? So I'm just going to repeat the definition of the subroutine here. So we have int subtract. It has got two parameters, int x, int y. And it only has one return statement, which is return x minus y, and close parentheses like that. Okay. So when I say we want to pass parameters on the stack, I mean from the perspective of the callee or the subroutine, the stack should look like this. X is going to take up 1 byte here, Y is going to take up 1 byte here, and then the return address is going to be here. So this is going to be the return address. So by the time the subroutine has control, I want the stack pointer to point to, this is register D, which is the stack pointer. I want the stack pointer to point to the return address. Actually, I take it back, sorry. Excuse me. I got the order flipped. I want this one to be Y and this one to be X. This Y, this is X. So X has a lower address than Y. Okay, so if this is the convention, and I just say that this is the agreement between the caller and the callee. If the callee is expecting parameters, expect it in this particular order. Okay, and relative to the return address as well. So I got two questions to answer now in terms of implementation. The first one is, what kind of code in the caller do I need in order to set up the stack like this before I jump to the subroutine? The second question is, from the subroutine's perspective, I know the stack looks like this at the label of subtract, But how do I make use of, how do I retrieve the value of x? How do I retrieve the value of y in order to do the computation in the subroutine? So I have these two questions that I need to answer. Is that okay? But the objective is to have this as the agreed upon format on the stack. Is that okay? So let me just make it very clear and just write it out, okay? So this is what the stack should look like at the entry point of subtract, the subroutine. Okay? So that makes it very clear what this picture is about. All right. So from the caller's perspective, the first thing I need to do is to push the value of y. Then I push the value of x as arguments. Then I push the return address. And then I transfer control or jump to subtract as a subroutine. That doesn't seem too hard. Let's see how we can do that. So keeping in mind of this picture, let me see if I can put it on the side like this. And then go back to my notepad so I can continue to work on that program. So I'm going to erase this one because it's not useful anymore. So from the caller's perspective, okay, so let's say we want to do something like subtract. We can use some constants. So let's say 5, 3. So we are subtracting 3 from 7. We'll see how we can do this. So the first thing we need to do is to push y first. So pushing y means we're pushing 3. So that's going to be a LDI A3. Decrement D to reserve that space for 3. STD3, A. So these 3 instructions together is pushing 3 on the stack, which is the second argument. And then we have something about the same for 7. LDI A7, decrement D, STD A. This is pushing 7 on the stack. So at this point, 3 is going to be at a higher location, and then 7 is going to be at a lower location. We have one more thing to push on the stack. We have the return address to push on the stack. So now we push that on the stack. So now we do another LDI, and we'll just call this main return, okay? And then we do exactly the same thing, decrement D, STDA. So this one is pushing the return address on the stack. So at this point, we now have all 3 things on the stack as agreed upon between the caller and the callee. I got my arguments, I got my return address. Okay, time to continue execution in the subroutine. So now I say, let's jump to the subroutine called subtract. And main return is going to be defined here because when subtract returns, this is where it needs to go back to. Okay, so when we get back from subtract, I need to clean up a few things on the stack. The return address is gone. The return address is the responsibility of the callee. So subtract would have cleaned up the location that was previously used by return address already. But I still have x and y on the stack. The subroutine being called doesn't clean up after the arguments. It is the responsibility of the caller to clean up after the parameters or arguments. Okay. So I will just kind of comment here. Okay. We'll say that 7, 3 are still on the stack. So that means we have to clean it up. I don't need to pop. In other words, I don't need to retrieve the content of X to a register and then retrieve the content of Y to another register because they are of no use of me anymore. So I just go like this and I just need to increment the stack pointer twice to clear out those locations, to mark those 2 locations are no longer in use. And that's exactly what I need to do is increment D, increment D. So this is deallocating space used by arguments. Now I'm truly done with calling subtract. So are we doing okay so far from the caller's perspective? Yep. Yep, go ahead.
Why, when you come out of the subtract function at main return, we still have 7 and 3 loaded, because wouldn't you have to use 7 and 3 within the...
You have to use it inside, but the agreement is the subroutine does not deallocate the arguments. Yep.
How do they access it without allocating?
We'll get to that. That's a good question. I'm glad you are already thinking ahead. But from this is kind of the agreement, you know, from the caller-callee perspective, is the callee only cleans up the return address, but the caller has to clean up all the arguments on the stack. Is that okay? All right. So now we can switch our perspective and go like, well, what if I'm subtract? What do I do to answer, you know, the question that you just asked? So we say, okay, here's the label subtract, which marks the entry point of the subroutine subtract. And just to kind of switch very quickly back to the browser, subtract is really simple. Okay, there's not much to do. We just have to retrieve what is x, what is y, do the subtraction, put the difference into register A, and we're good to go. Is that okay? So it can be done in a variety of ways, but this is the way that I recommend. And let me show the stack again, and then go back to my code here. So the first thing I do is a CPR instruction, CPR CD. In other words, at this point, C is a copy of the stack pointer. And the way I look at this is whatever C points to is the return address. So let me see if you guys are comfortable with this notation. Because C is a copy of D at this point, D is pointing to the return address because that's the agreement between the caller and the callee. So when I make a copy of register D to register C is also pointing to exactly the same place, which is the return address. So in C notation, it simply means C is pointing to the return address. Now this is a double equal because I'm simply stating the equality. I'm not expressing an assignment operation. I'm not intending to change. I'm simply stating that what it is pointing to is this value. Okay? All right. So now I'm going to do some tricks. Okay? So I would go, the first thing I do is let's increment C, not D. Okay? We want to keep D pretty much the same throughout the execution of the subroutine. But I can mess around with C because, you know, the agreement is the subroutine can mess around with any register other than D until it has to return, then register A contains the return value. So right now I can mess with any registers, A, B, and C. They're all free for me to use. Okay? But I will just increment C at this point. After the increment of C, what do you think C is pointing to? Exactly. Oh, isn't that one of the things I need for the subtraction? Let's pick it up. What do I mean by pick it up? Just do LD. Put it into a register, like that. So now at this point, A is the same as whatever C points to, which turns out to be X. Kind of cool, useful, okay? Then I move on and go like, okay, let's increment C one more time. So if I increment C one more time at this point, what is it pointing to? It's pointing to Y. Very good. Isn't that one of the things that I also want to pick up, you know, to do the subtraction? All right. Oh, cool. Let's put it somewhere. So now we have B being whatever C points to at this point, which is parameter Y. All right. So at this point, we got both of those numbers in registers. We got X in register A, we got Y in register B, and what I'm supposed to do is just a simple subtraction. Okay, so let's do a subtraction. SUB-AB, okay? And guess what? They're already in the right order because we are supposed to report back X minus Y. Well, A is X, B is Y. So A, X minus Y is now stored back into A. And guess what? A is the register that we need to use to return a value. So we are done. I mean, this one single instruction is doing several things. It's doing the computation, but it's also putting the return value into the right register before we return. Excellent. So now we can just go for the usual return code, which is LDBD increment D. So we are now popping pop return address to register B, and then the JMP will continue execution back in the caller where we left off. Is that okay? All right, well, it looks okay, but we should test it, right? So let's go ahead and test this code. And to finish this program, there's one instruction that I need here. This line obviously should be gone because it's just a C code. So we need to do a SUBDD to initialize the stack pointer. That's pretty much the only thing we need to do at the beginning. And at the very end, we need to do a halt instruction, because otherwise the program will just keep going into subtract, which is not the intention. So we have to put a halt instruction at the very end of main. Are we doing okay so far with this? Okay, so let's give it a try. So now we do a Control A, switch back to the browser. I'm going to close the browser and just reopen it. The reason why I'm doing it is because I have learned that Chrome is not very good at cleaning up. So over time, your Chrome can potentially use a lot more RAM than it should. So we'll restart Chrome at this point. I have to move everything out of the way to get to my icons. Come on, move. There we go. And I can retrieve all the tabs by using this thing. It's called Session Buddy. It's really handy because you can just click it and it remembers that we have recorded 6 tabs from 12 minutes ago. So you just click it, you click open, and if I had those tabs in different windows, it will open those in separate windows as well. So we can just open it in this particular window. So we get everything back. So we can retrieve the context from before. All right. So now let's go to, I might have lost my session though, that's the problem. Yeah, every time I restart the browser, it wants me to sign in again. Because the cookie itself is a per session cookie, it doesn't persist. That's fine. We go to apps, go to Google Drive. I think a Chromebook can beat this computer in terms of speed. No, not a URL. That does not compute. I forgot to copy from my mousepad first. There we go. Paste. There we go. Much better. Okay, this is a leftover from previous, so I'm going to delete it so it doesn't confuse us. Okay, it's not going to cause any problem. It's just confusing. And then we go to RAM file, download as. And I'm just going to call this subtract. There we go. And we'll start Logisim. And put it into RAM. So, okay. So we got the program for the most part loaded, ready to run. You can run the program and look at register A. By the time we get to the hold instruction, it should be a 4. Okay? But that only verifies that the program did work. Okay? But it doesn't show you exactly how it worked. How did the stack pointer change? What was stored on the stack? When do we change the stack? When do we increment? When did we decrement? And so on. So, well, the best way to get a full understanding of how the stack is being used and how the stack pointer is changing along the way is to use the logging feature. This is kind of how you study this kind of material. It's not so much to read the material. The material, when you read, is really not that long. Okay, it talks about the concept itself, which is not terribly complicated. But in order to actually understand and visualize and see examples of the whole thing running, a trace can be very, very helpful. So what we do is we trace a few things. The program counter is always, almost always, something you want to trace. In this case, register D inside the register bank is also something really kind of important. So we look at register D and say, yep, let's keep track of that because that's our stack pointer. And I change everything to base 16 because otherwise the default is base 2, which is not very friendly. So we switch everything to base 16. If you want to track register A, B, and C, that's fine too. Okay, especially register A, it's kind of useful because it's used as the return value of a subroutine. So we'll go ahead and track that too, and change the radix to base 16. And then we can look into RAM. So in this case, we look at RAM, and we think about how many locations should we be using. Well, let's see. Location 255 is used for the second argument. Okay, so we change the radix to 10 because it's a base 10 number. Location 254 is used by the first argument, which is x, which I also specify in base 10. Location 253 is used as the return address. We'll look at it as a base 16 number because it's an address. And I think those are the 3 locations this program should use. Okay, no other locations on the stack should be used in this program. But I'm going to track 252 as well, just in case. If I see location 252 being changed, then I know the program is not doing what it's supposed to, or my understanding of the program is not correct. But either way, it is information. Okay, so I'll keep track of that one too, and we'll change the radix to 16, because that's kind of the default. So I would put these items as kind of the minimum to track for a program like this. Okay, and we'll put it in the file as well, because this way we can after the fact analyze the code as much as we want to. So we'll go ahead and put this into subtract.tsv because it's tab separated value. And now we are ready to go. So Control K, start the execution, and at this point it has stopped. You can tell it has stopped because there's no activity in the RAM, and on top of that, you can see the program counter is kind of stuck, as well as the microcode pointer. So the microcode pointer is now stuck at 010, which means it is executing the halt instruction over and over again. It cannot get out of the execution cycle of the halt instruction. If I look up location 11, not 12, but 11, that should be the halt instruction as well. Okay. Okay, so the whole thing is done. Let's press Control K, stop the whole thing, and then we'll use a spreadsheet to take a look at the content of the trace. So in this case, I'm going to use LibreOffice Calc and open up subtract.tsv. Unfortunately, it always interprets numbers. So it doesn't explain what that is. Detect special numbers. Well, I'll give it a try. Let's see. Yeah, there's no option not to detect, numbers, because oh, okay, look at that. That looks okay. Well, let's see. Now, it's still not doing it correctly because these numbers are still interpreted as numbers, which is not what I wanted to do. But that's okay. We'll just call this stack pointer, which is register D. This is register A, 255, 254, 253, 252. And now I can resize the columns so they don't take up this kind of space, which is not needed. And double click. Now we get a kind of easier way to look at the whole thing. Like so. All right. So the first thing we want to look at, this captures a lot of details. But what is important to us is when the stack is fully set up. So we can see column D now has the second argument, the 3. Location 254 now has the first argument, which is 7. And then location 253, the lowest location, has the return address. But how do we know 0F is the return address? Well, you can go back to the assembler, go to the Assemble tab, and then you go to main return as a label definition. And basically, we want to look at the address of this location, which is in column W. So on column W, you can see that 0F is the label after main return, which means the label main return is 0F. So that means this location here is also the return address that is now stored on the stack. Is that okay? So we go through the computation, and we also can tell from the program counter that there's a jump from 0E to 12. Because from 0E, even if that instruction has 2 bytes, it should only go to 10. But it's not at 10 next, it is at 12. So that means this jump is a JMP instruction, can only be done by a JMP or some conditional branch instruction. So that means there's a strong suspicion that 12 is the beginning of subtract. Well, let's double check. So we go down a little bit to take a look at the subtract label. And sure enough, the subtract label is at 12 in hexadecimal. So this is the sort of thing that, the first few times you go through the trace, you want to kind of read the trace and confirm these observations. Okay. All right. So once we are at location 12, we start to read things into register A and register B, starting with register A here, and then we have register B here. So we are expecting register A to have 7 and register B to have 3 eventually. So we go back to the spreadsheet, and then we observe the values in register A. I didn't keep track of register B, but you can see register A ends up with a value of 7, but I didn't keep track of register B, so we can't see that. But we also see that, at this point, it is now 7 minus 3, which is 4. The location is 18 in hexadecimal. So we have a strong suspicion that 17 is going to be the location of the subtract instruction that computes the difference. But it's always a good idea, at least for the first few times you go through the trace, to make sure. So now we look down the program a little bit. We get to the subtract instruction, which is this one here. And you can see how the location of this thing is at 17. And I think that's what I said, right? 17, because the program counter was 18. Okay, cool. We can also see how the stack pointer is changing too. So when you look at the stack pointer remained exactly the same throughout this time. And then only at this point it started to change. So this is an increment of the stack pointer because it went from FD to FE. So that means the address 19 should correspond to the increment of the D register, okay, which is still in the subroutine. And then you can see also how the program counter went from 1A to 1B, which is okay because it's sequential, and then from 1B it went back to 0F. But we already know what 0F was, right? 0F was main underscore return, which is the label of the place to return to from the perspective of the subroutine. So now that we are on at 0F, we are back in main, and then main doesn't really have a whole lot of stuff to do except to clean up the stack. What do I mean by cleaning up the stack? Look at the stack pointer. The stack pointer is now FE, then it increments to FF, then it increments to 0. Now the stack is quote-unquote balanced, because at the very beginning of this entire program, the stack pointer was initialized to 0. Now it is going back to 0, which means the stack is once again empty. There's nothing in it anymore. So that's the way we like it, because we don't like the stack to be unbalanced with stuff that really should not be there.
The stuff is still there, it's just not training on it anymore.
That is true in this specific case, but not generally true.
Most programs will clean it up as they go.
Well, so the thing is, okay, so I'm glad you asked that question because we can kind of digress to a concept called interrupts for the next 20 minutes or so. We got time to do it. So what we'll do is we're going to go to the tablet because this stuff is best explained using a tablet in an interactive way. All right, but before we even do this, let's think about what do you think the computer is doing in the good old days, okay? Remember those, K-Pro. I mean, you guys don't remember it because it was before you were born. So in the very old days, there were computers and there's only one prompt, okay? The computer can only do one thing at a time. And you type, dir, and it shows you the files in a directory and stuff like that, okay? So if you think about it, how does the computer know that you just typed the letter D on the keyboard? And then the I, and then the R, and then the return. That's okay. Basically, there are I/O ports. Okay, so when you press a key, the program can detect a change at a quote-unquote memory location, and then it grabs that key code, and then it can make the keyboard ready to transmit the next key code and so on. Okay, but that's even besides the point. In the good old days, the computer, the program itself, is going to ask the keyboard controller all the time. It's like, do you have a key for me? 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 So it would just be stuck in an infinite loop asking, do you have a key for me? Is that okay? It seems pretty logical when there's only one thing you do on this computer. You can just spend all eternity asking that question until you say, yep, I got a key, and this is the key code of a lowercase d character. Then the operating system takes that key code and go like, oh, okay, I'll put it into a buffer. I see that this is not a return key. I'm not supposed to interpret what you have just typed on that line, so I'm going to keep asking you again, do you have a key code? Do you have a key code? Do you have a key code? Okay. So with the older PCs, they're running at 4.77 megahertz. So this question is going to be asked in, I guess, some kilohertz frequency, hundreds of kilohertz frequency. Okay, which means each second that question is repeated 100 or several 100,000 times. How fast can you type? So, but it's okay because the computer has nothing else to do. So this is called polling, okay? P-O-L-L-I-N-G. The approach is called polling, which means the computer program, it just keeps asking, is there anything for me to process, okay? Well, it works until Windows 2.0 came along. So Windows, even in its earlier stages, was supposed to be multi-processing. It's like, oh, you can open up Notepad over here and play Solitaire over here. Those were one of the two original apps in Windows, Notepad and Solitaire. And it was cool, absolutely cool, that people could go like, look, I can type my program a little bit here, and then I keep playing Solitaire over there. It was considered super cool back in those days, because before Windows, you truly can only do one thing at a time. Okay? So now you start to open up a command prompt in Windows, okay, which is kind of like just a graphical version of the command prompt that takes up the entire screen. And then everything comes to a halt. Nothing works. Why? Well, as it turns out, Notepad and Solitaire are cooperative. Notepad basically says, do I have a key to process? No. Okay, I'm going to give up my control to whatever is next so the other program can do some processing. So control is now passed to Solitaire, and then Solitaire says, did anything got clicked in the, when I wasn't paying attention? No, nothing got clicked. And then the control get passed back to Notepad, which then asks, did I get a key code? No. So it gets go back and forth, and no one is hogging the resources, right? And then when you start up a command prompt, like what we call a DOS prompt, the DOS prompt is still doing the same code as before, using polling, right? So the DOS prompt, once it gets control, it just does not relinquish control. It just goes like, I'm just going to keep asking the keyboard controller whether there's a key code or not. I'm not letting go of anything. So that approach didn't work very well. Now that approach would not work very well on your cell phones either, because if you think about your cell phone, okay, so and on most cell phones now, you have a like a fingerprint detector thing to open it up, or a power button, right? So think about your cell phone and go like, how does the cell phone know that I just press the power button or have put my finger on the fingerprint sensor, so it knows, oh, maybe I need to turn on the screen and restore this app, blah, 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 and a whole bunch of stuff, right? But this is a relatively simple operation. I just push the button, okay? But what if your cell phone is doing polling and keep asking the hardware device, was that button pressed? And remember, your cell phone is not running at 4 megahertz anymore. Most cell phones are now running at what, 1 gigahertz-ish, around that, depending on whether you want a power save or whether you want performance. But it's still running at hundreds of megahertz. In other words, it will be asking that dumb question hundreds of millions of times per second. How fast can you press your power button? Okay. Then what is the big deal? You cannot, fine, I cannot press the power button that quickly. So what is the big deal? Your battery won't last 15 minutes. Because when it's active like that, asking those questions is taking up a lot of battery power, because the processor and the RAM and all the other components have to be actually working pretty hard even to answer that dumb little question. Because it has to answer that dumb little question several hundreds of millions of times per second. Is that making any sense? Okay, so the polling method doesn't work because it chews up too much power. It is not playing nice with other applications running at the same time. So what do we do next? Well, the approach is called interrupt-driven or event-driven approach. In other words, your processor, for the most part, doesn't even care that you have a keyboard attached, or that you have a power button attached, that you have a fingerprint sensor attached. The processor is just going like, do I got anything to do? No, I'm going to go to sleep. I'm going to take a nap, okay? What does it mean when your processor goes take a nap? It means it is not clocking, and it is not using up too much juice. It might take up a little bit, but not a whole lot, okay? So that means, if your phone is off the network, it's off, 4G, it's off, from cellular, signal, and you do not have anything scheduled for it to wake up and do stuff, your cell phone probably can last a day and a half easily, because there's nothing to do, okay? So it doesn't take up a whole lot of power just to maintain the current time and all the other really essential stuff that your cell phone needs to maintain. Is that okay? So if the cell phone is not paying attention and keep asking, did someone press something on the keyboard, or is the power button pressed, or is your finger on the fingerprint sensor, then how does it know when I do press a button on the keyboard? How does the processor know, so that it knows how to grab the key code and attach it to the command line, and if it's an enter key, it will process it and actually do something? How does it know? It's called interrupts, okay? So almost every single hardware device on the modern computer can trigger an interrupt. What is an interrupt? Well, it's kind of like this. Okay, So let's say this line is representing what your processor is doing, okay, normally, okay? If you have anything for it to do, like you're transcoding a video, okay, so that's going to be the background thing that it's doing. It's chewing up all the processing resources, you're transcoding a video. And then you decide to press a key. So when you press a key, what happens is it switches to a different chunk of code to execute. So this is this is your transcode subroutine or code process, and it will suddenly go to another chunk of code because you pressed a key. So I'm gonna use this symbol here and say that it's triggered by you pressing a key. Okay. So when you press a key, the computer, the processor, has an internal circuitry to say, oh, there's an interrupt. I'm going to switch to another subroutine. It's going to quote unquote call a subroutine. So this is basically a subroutine. And when this subroutine executes, it will grab the key code, put it into a buffer, do something with it, and then it's going to go back and like, oh, okay, we can continue the transcoding now. Okay. So this part here, this is called an ISR. ISR stands for Interrupt Service Routine. For the most part, look at it as a subroutine. It's a subroutine that is not called. It is not called by any instruction. It is not called by any program on your computer. It is quote unquote called by the hardware. So your keyboard controller in this case is the active agent that is quote unquote calling that subroutine. Is that okay? So what other hardware devices do you think will be calling, quote unquote, calling interrupt service routines? What kind of devices is on a cell phone? Okay, don't even think of a computer, think of a cell phone. We got the fingerprint sensor, we got a touch sensor, right? We got audio sensor, okay, mic. We have Wi-Fi communication. We have 4G communication. There's a clock, there's a timer in the inside that keeps track of time all the time. So there are a lot of stuff that is actually going on, and some of that stuff is interactive. It's triggered by external events. Okay, so when I move my finger on my phone, it's causing, each change is causing an interrupt. It's like this. Every time I touch, every time I move my finger across, even if I press a little bit harder, the capacitance changes. And if the capacitance changes, then it will also change the value that the touch sensor is going to receive. Every little change is causing blips like this, blip, 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 like that. Okay? Okay, but how does this have anything to do with the topic that we are talking about right now? Okay, so think back on Monday. What was the topic on Monday? It has to do with subroutine, calling, and returning, right? And the stack. Okay? And what was the last topic before I quote unquote digressed to talk about interrupts? What triggered me to talk about interrupts? The stuff that is below what the stack point is pointing to, right? Okay. So now let's take a look at the picture of the stack here. So this is the stack. This is the portion that you are using, okay? So we'll just say transcode stack. In other words, this chunk of the stack is currently being used by the transcode program, okay? It's doing its hardest job to transcode a video. It's going to take 30 minutes, okay? So it's just humming along in the background. And now you just type something on the keyboard, or you move the mouse, or you talk on your mic, or there's a packet coming in from your Wi-Fi router. Okay, any one of those things is going to cause an interrupt. When I describe an interrupt, what was its mechanism again? It's calling an ISR. So even though there's no actual instruction to divert control to the ISR, the mechanism is the same as calling a subroutine. Okay, we have been talking about calling subroutines on Monday as well as today. What does it do to the stack when you're calling a subroutine? It has to save the return address, right? So in this case, it will save the return address of the last opcode, of the next opcode to execute on the transcode process. It has to save it, then it can safely go and execute the ISR of whatever hardware device that's causing the problem, causing the interrupt. And when it's done processing that hardware request, it will continue, come back and continue the transcode program. But where is it going to continue? It will retrieve that location from the stack so it can continue to process your video. That is the same mechanism as calling and returning, just like the same thing that we have been talking about. So that means when the interrupt happens, okay, so let me make it even more clear. The stack pointer is pointing to the very last thing that you pushed on the stack. So whatever the stack pointer is pointing to is quote unquote in use. So in this case, whatever the stack pointer is pointing to right now is in use by the transcode stack, by the transcoding program. Is that okay? I'm going to use a different color. When the interrupt happens, then it go like, okay, I'm going to have to push my return address. So this is the ISR return address. Then your stack pointer is moved to here, and possibly lower, depending on what the ISR has to do. It might use up like digital space because it's complicated to process a TCP/IP packet or something along that line. You have no idea how many bytes the ISR is going to use. Neither should you care, okay? Because what is happening is when the ISR is all done, okay, so let me just kind of assume that the stack is going to be, it's going to use up this much stack, okay? So the stack pointer eventually will get as low as here because of the ISR. When the ISR is done, when the interrupt surface routine is done, then it will clean up the stack just like any subroutine. It will clean up its own mess, including the return address, because it needs that to return back to what your transcoder program is executing. So what's happening is the stack pointer would now go back to where you are when the ISR is done. So from your perspective as the transcoder program, it is as if nothing happened. Okay? You're not even supposed to be able to tell whether an interrupt happened, between instructions. Is that okay? But what that means is whatever is below what your stack pointer is pointing to can be changed without you knowing it. Is that okay? So that means never assume the content below where the stack pointer is pointing to remain the same. If that is still important to you, do not move the stack pointer up until you are done with that content. Because the moment you move the stack pointer up, the interrupt can happen immediately and make use of that content, and then it's gone. Okay? So is that kind of explaining why we kind of have to keep an eye on where the stack pointer is, and do not assume anything about the content below where the stack pointer is pointing to. But if you run programs in the toy processor, this never happens, because the toy processor has no actual circuitry to detect interrupts. Okay, I barely got enough time and in complexity to put in what needs to be there, so the interrupt mechanism is not a part of the toy processor. And that's the only reason why it doesn't happen like this. And somebody is going to try this on an actual program, on an actual computer, like a PC, running Windows or even Linux, okay? And they observe and go like, nope, I never observe anything below where the stack pointer is pointing to being changed. And I keep slamming on the keyboard, moving my mouse, and doing all sorts of things, and yet it doesn't seem to be corrupted. What's going on? Well, that's because Linux, Mac OS X, and Windows, they are all protected mode operating systems. So that means when an interrupt does happen, it's not using your stack. It's using the kernel stack, which is somewhere else. That's why you do not see any changes below where the stack pointer is pointing to, because the interrupt happens, it does clobber parts of a stack, it uses part of a stack, it's just that it is not your stack. Okay? So you might think, oh, so that means I don't have to care about this sort of thing because, hey, I'm just going to write some applications here. Well, what if you're dealing with an Arduino? Okay, what's an Arduino? An Arduino is a single board computer that you can program using C and C++. Okay. Okay. What about that? It doesn't have an operating system. Now you can still call, you can still return, you can write C code just normally. Okay. But you cannot assume anything below where the stack point is pointing to remain the same anymore. Because on an Arduino, there's only one stack. Your app is using that stack. The interrupts are using that stack as well. And you don't have any control over that. So that means if you need to resort to use assembly code on an Arduino program, then you have to be careful about how you use the stack. Is that okay? Does anyone know what an Arduino is or know what you can do with one? Okay. Oh, you can do, the program space is not that big, so it cannot really hold and store really complex programs, but you can do a lot with it. So I just want to show the class, Arduino. What is the smallest one? Huh? Uno? Yep, the Uno is pretty small, but I don't think the Uno is the smallest.
They have one that's like designed for making wearable.
Is it Nano? Yep, I think it's the Nano. And we want to look at the scale. Looking for measurements. There you go. This is a good picture. I think that's a quarter. So that's basically the size of an Arduino. It is C programmable. You can actually pack quite a bit of C code onto one of these things. I believe it has 32 kilobytes in the flash memory of one of these devices. And you might think, 32 kilobytes. When was the last time you saw a program that has 32 kilobytes? Doesn't sound like a lot. Trust me, if you're writing C code and complex C code, 32 kilobytes is a lot. I used to teach a robotic class where robots have to self-navigate, maintain a map, and use quote-unquote AI algorithm to find the shortest path. Even those programs only can fit into like between 32 to 48 kilobytes of space. Okay, so 32 is a lot. You can actually do a lot of stuff with 32 kilobytes of program space. And the whole thing is only about the size of 2 quarters, okay? And it is not expensive. How much is one? Well, it's a little more than $5, but I don't think it's too expensive. We'll just go visit it. This one is expensive. I don't think it should be that expensive. Farid, do you remember? Because the hub uses Arduino a lot. So we can look up Arduino Nano price. There we go. So this is the development kit. It's not the entire thing. Yeah, so there's a whole bunch. 10 pack. Yeah, let's buy 10 of these. So a 10 pack is $36. So that means one each is only $3.60. Can't even buy a good cup of Starbucks with that much money. So next time you go to Starbucks, you just think about it and go like, whoa, some people can buy 2 Arduino Nanos with 1 cup of coffee. So that's, if you're not exposed to these concepts, I highly recommend looking into these things because they are a lot of fun to play with. And then the entry point is the entry, how should I put it? The learning curve is really shallow. If you already know C and C++, it's really easy to get into it. All right. So that's going to be the end of today's lecture. I have the new lab activity already opened. So by the time you get to the lab, it's already going to be open. And if you have questions about the lab, we can answer. I can answer those